Hi, in a previous video, I explained the rational root theorem, the way it's usually given as homework or quiz or exam question in an algebra class. In this video, I'll show how it's more powerful than first appears. I will use it to prove this fact about the radicals of integers. The real root or radical, mth root of n, where m and n are both integers, is either an integer or an irrational number. In other words, it will never be a non-integer rational number. Another way of saying it is this: if the real mth root or radical of an integer n is not an integer, then it has to be irrational. Before continuing, let me go back and make sure we all understand the words being used here. If you already know the concept of integers and irrational numbers and such, go ahead and use the scroll bar on YouTube to skip ahead. So these are the common sets of numbers. The natural numbers, written as n with a double stroke, consists of 0, 1, 2, 3, etc. On the number line, these are the natural numbers. By the way, high schools in the US teach that the natural numbers start at 1. There's a reason for that, and that's okay. But mathematicians start the natural numbers at 0, what the high schools call the whole numbers. Integers are like natural numbers, but they can be negative as well. 0, 1 or negative 1, 2 or negative 2, 3 or negative 3, etc. Goes on forever both ways. The symbol for this is a capital letter Z, again with the double stroke. So the integers include the negatives back on the left as well. Next are rational numbers. The set is written as a letter Q, and it consists of all possible fractions of integers: 1/2, -3/4, 5 2/3, etc. So it's all the possible P over Q, where P and Q are integers. Note that integers are rational because a number like -5 is the same as -5 over 1. And then the set of all the possible numbers on the number line is called the set of real numbers, and is written as a letter R. So we have this Venn diagram. The natural numbers start at 0 and going on positive. It's a subset of all integers, which in turn is a subset of all rational numbers. And everyone is a subset of the real numbers. Well, and then there's this part right here, the part that is a real number but not a rational number. These are the irrational numbers. And they don't really have a symbol. People just write it as the real numbers that are not rational. Now back to our theorem. The real radical nth root of m, where m and n are integers, is either an integer or irrational. In other words, never a non-integer rational number. Some examples: square root of 9, that's equal to 3. That's an integer, no problem. But square root of 8 is 2 point something, and it's not an integer. And the question is it a rational number or an irrational number? What this theorem says is that this one has to be irrational. If it's an integer, then good. But if not an integer, it has to be irrational. Let's go back to the Venn diagram we saw earlier. What the theorem says is that sometimes you have radicals that are integers, maybe positive, maybe negative. But when it's not an integer, it will have to be irrational. It will jump all the way to that outside set of irrational numbers. It will never be in this area of the rational numbers that are not integers. That's what the theorem is saying. So I'm going to prove it by using the rational root theorem. So let's write the rational root theorem. Given a polynomial equation with integers coefficients, then if the equation has a rational root p over q that's fully reduced, then p is a factor of a naught and q is a factor of a n. A naught is the constant term and a n is the leading term. And I like to think of it like this, that any rational root of the equation would have to be of the form plus or minus factor of constant divided by factor of leading. There are two different meanings of the word root that we're talking about in this video. This word here means the solution of an equation. Whereas in this notation, when we're talking about the nth root of m, this word root means the radical. So there are two different meanings, but actually what I'm going to do right now is I'm going to use this to prove that by creating a relationship between these two meanings of the word root. Proof. I'm going to give this radical a name. So let b equal to nth root of m. If b is an integer, no problem, I'm done, because the theorem says it can be an integer. If b is irrational, I'm also done, because the theorem says b can be irrational. The only question is what happens if b is rational? Suppose b is rational. Starting from here, I'm going to raise to the power n both sides. So b to the nth power is equal to m. And then I subtract m both sides. I have b to the nth minus m equals to 0. So what it means is that b is a solution or root of the equation x to the nth minus m equals 0. Well, what about this equation? Well, first of all, it's polynomial. And what are the coefficients? There's a coefficient here of 1, and there's a coefficient here of negative m. It has two coefficients, and they're both integers. One is an integer, and negative m is an integer. Since the equation is polynomial with integer coefficients, that means the rational root theorem applies. Meaning b is going to be of the form p over q, fully reduced, where p is a factor of m and q is a factor of 1. Constant over leading. Just to be precise about it, I'm going to change this to negative m. What kind of integer is the factor of 1? 1 or negative 1. That means b is equal to plus or minus p, which is an integer. We suppose that b is rational, and then we've proven that b is an integer. Therefore, b is not a non-integer rational number. Which is what we need to prove. In math, once we've arrived at the point where finish a proof, a lot of people would write the word QED, which is short for a Latin phrase that means the thing to be proven. We've arrived at the thing we needed to prove. Hope that's fun. Thanks for watching. Subscribe for more contents. Bye.